Today we're going to talk about what is CDC. We're going to have a bit of an overview of that, as well as talk about what is Debezium and how does it work and how do we use it. But then we're going to spend the majority of our time today talking about the streaming patterns, the outbox pattern, the strangler fig pattern, and the saga pattern. How many people here have heard of these patterns before? Okay, a couple of folks, cool. And then after that, we're going to talk about why we need these patterns, what problems are they trying to solve, how do we use CDC with those patterns to solve those issues, and then we'll open it up at the end for some discussions and Q&A. For those of you who may not know who I am, my name is Cranford. I am a principal software engineer at Red Hat. I've been there for 7 years, and I've had the wonderful privilege of working on several open source projects over that time, including Hibernate and Quarkus, which I'm assuming most of you have probably heard by now. Over the last 4 years, I've been working on the Debezium project, and I've contributed to quite a number of Debezium's milestones, including its 1.0 and 2.0 releases. I've also been responsible for the PG output decoder implementation for gathering change events from Postgres on cloud environments, as well as the Oracle Log Miner, CDC connector, and most recently, the JDBC Sync connector that the Debezium portfolio will start offering starting this month. So let's get started into what we are all here to talk about today, and that is change data capture. So what is it, and how does Debezium fit into this picture? On the left-hand side, we have two databases. We have a MySQL database, and we have this Postgres database. And these databases, they use what's called transaction logs, and these transaction logs are responsible for tracking all changes that occur in that database. All the inserts, the updates, the deletes, the schema changes, etc., are all captured in this log. And these logs are really important for databases because they typically use these for recovery purposes, but they also use this for replication. And what we're going to do is we're going to use Debezium to tap into these transaction logs, and we're going to convert all the entries in those transaction logs into change events that we can then send to our consumers. Now on the right here, we can see that we have 3 different consumers. Why are we wanting to send these guys these change events in the first place? Well, we may have a search index that we want to keep updated with our operational data that's in MySQL or Postgres or any other relational database. And we want to make sure that we're keeping the search index up to date with extremely low latency. If we were to schedule a batch job or a cron job or use some ETL tools in order to be able to do this, we sometimes would have to schedule these to run on some interval, and that's usually not what we want. We want to be able to get those change events into our search index as quickly as possible, preferably right as that change occurs. You may have a cache, or you may have a data warehouse that you're also wanting to move your operational data into for some type of analytical processing. And we're noticing that with frameworks like Apache Pinot, that users are really trying to build these real-time dashboards and analytical tools for their user-facing applications, and being able to leverage change data capture in Debezium to move those change events into that the application for that additional processing is extremely important. And again, coming back to the point, we really want to do this with extremely low latency. Now, on the left-hand side here, we have 2 connectors. We have the MySQL connector and we have a Postgres connector. And these connectors are really what's the bread and butter of Debezium. They're responsible for tapping into those transaction logs, and they are going to convert all of those entries in the transaction logs to change events. Now, we could, in theory, connect Debezium up to our consumer applications. We could connect it to our Elasticsearch and send it directly over there. But there's reasons why we probably don't want to do that. There's a number of benefits that we can get if we decouple that process, and usually our users prefer to use something like Apache Kafka. And that gives us the ability to have a distributed committal log that is capable of being able to retain those change events for periods of time that's really entirely configurable for you. And so if we think about this for a moment, if we were to say, set these topics to have infinite retention, Apache Kafka gives us the ability to have a ton of optionality and functionality available to us. First of all, we can gather those change events from those operational databases once, and we can deliver those change events to multiple consumers. This provides us the ability to make sure that we're keeping our overhead on those databases extremely low. For some databases, there's more overhead with reading transaction logs than others. And then it also allows us to be able to send those change events over to those consumers in a delegation type way. The other thing to keep in mind with this is that it also allows us, depending on the amount of time we keep those change events inside Apache Kafka, we can actually consider introducing other types of consumers in the future, and those consumers can take advantage of all of those change events that we've gathered over time. And then that way you don't have to necessarily be worried about what type of consumers you need to develop for future applications, because Apache Kafka can help you prepare for that if you need. In addition to this, there's also this component called Kafka Connect, and this is the runtime that runs these connectors, and it's responsible for making sure that these connectors stay running and making sure and giving the ability for these connectors to send data into Apache Kafka as well as consume data out of Apache Kafka. Now, what is Debezium? We've kind of talked about, it at a very high level, but ultimately what Debezium aims to try to be is a CDC platform. Yes, we can read those transaction logs and we can generate change events, but Debezium offers you a ton of other functionality, such as snapshotting. This allows you to be able to gather all of the current records that are in your database, and you can send those as an initial dump over to that consumer application. So you can seed that database or seed that search or whatever it is you want to send those events to. It also offers you the ability to filter those change events based on any type of configuration that you wish to configure. It also provides a ton of out-of-the-box functionality, including the outbox pattern that we'll talk about today. And it also provides converters for different types of message formats. Perhaps you want to be able to send those change events in cloud events format instead of Debezium's native format. You can do this all through configuration. And it also comes with its own UI. So if you want to be able to deploy a connector inside Kafka Connect, you can do this through a very easy to use UI interface. It's open source, it's Apache license, and it has well over 450 active contributors, some of which, yes, are Red Hat engineers, but many of them are also from other communities, such as the Apache Cassandra community, the VTest community, and most recently, Google has begun contributing to the Debezium project, which is kind of cool. Now, as I said, Debezium reached its 2.0 milestone late last year, and even prior to reaching that milestone, it was already being seen as a stable solution. There were already tons of deployments in large production environments, such as Reddit, such as Shopify, and Ubisoft, just to name a few. Now, with Debezium, when we talk about these connectors, there isn't just one connector that you can deploy and use, unfortunately. Every one of these database vendors decides they want to use a specific format for their transaction logs, and they make that format available through whatever APIs that they wish. And so Debezium has done the research. They have a connector for each one of these types of databases. Now, the benefit to this is for you as a consumer or as a user, Debezium unifies all of those change events. So for you as a consumer, you don't need to worry about, is it coming from Postgres? Is it coming from Oracle? Is it coming from MySQL? They all come through with the same uniform format. Now, MongoDB is a little bit different because it's a NoSQL data store, but for the relational databases, they all follow the same paradigm. But there are also community-led connectors underneath the Debezium portfolio, like the VTest connector, which supports horizontal scaling of MySQL. There is the Cassandra connector, which supports Cassandra 3 and Cassandra 4. And then most recently, Google has introduced their Spanner Cloud connector that's based on Debezium. And this really kind of signifies, when we talk about this from a community point of view, with these community developers and organizations and communities, when they are choosing to use Debezium, it's really sending a clear message that Debezium has become or is becoming one of the leading de facto CDC frameworks in the industry. And in order to solidify the fact that we want to be a complete CDC platform, we have chosen to introduce our own JDBC Sync connector, which allows you to be able to ingest native Debezium events directly into any relational database. And so you really are starting to get a full platform solution from start to finish, from the source to sync side of being able to handle change data capture. But while 90% of our users typically deploy Debezium on Kafka, you don't have to. And we understand that there are reasons why you may not want to use Kafka. You may not be a Kafka shop. You may be a Microsoft shop and you want to use Azure or Event Hubs or some other messaging infrastructure. So there are tools and there are ways in order to use Debezium for that type of a situation. Now, one way you can use Debezium is embedding it inside your Java application. Debezium is written in Java, in fact, and so it's really easy to embed it as a library inside your own application. And this typically is an advanced feature. Most users don't do this, but there are reasons that you may need to do this. Perhaps you want to do some low-level operations on those change events. And so by using the embedded engine, you can do this. And if we look at frameworks like Apache Flink, for example, their CDC connectors, which are based on Debezium, do exactly this. They use the embedded engine for their CDC solution. But you can also choose to run Debezium using Debezium Server, which is a Quarkus ready-made runtime that, in effect, carries on the same kind of role that Kafka Connect does for Kafka users, but one major difference. This allows you to be able to send Debezium change events to any other type of messaging infrastructure. Like if you want to send it to Amazon Kinesis or Apache Pulsar, Google PubSub. As I said, event hubs, those are all opportunities and options available to you. There's nearly a dozen different adapters in the Debezium server repository to support any number of messaging infrastructures, including even sending it directly to Kafka if you wish. Now let's talk about Debezium's events and what those change events kind of look like. And I want to preface this by saying that on the right here, I'm talking about this from a semantical point of view. You may want to serialize these events into Kafka or your messaging infrastructure using any other type of serialization. You may choose to use JSON, but you may choose to also use things like Avro. But we're going to be looking at these events purely from a semantical point of view. And one of the most important things that most consumers are always interested in, of course, is what's the state change? What happened in that database? And you can get this by taking a look at the before and after state in these change events. As you may think, before basically represents the state of that row before the change was applied, and of course after is the representation of that row after the event was applied. If you have an update event, for example, you would have both of these. If you have an insert event, you would only have the after. And naturally, for a delete, you'd only have the before state. But it's not just that information that is available in these change events. There's tons of metadata that we also provide to you that may be of interest, depending on what your consumer happens to be. We can tell you what was the database type or the connector that was used in order to gather that change event. We can tell you what is the timestamp that that event occurred inside that database. You can find out whether or not the event that we're giving to you occurred from within the snapshot phase or the streaming phase of the connector. And then as well as what was the table that it originated from or is related to, as well as the position in the transaction log. We also give you information about what type of event it is and when we process the event. And just with this information alone, you can discern directly from the event what's the latency of this event. How long did it take from the time the database wrote this to the transaction log? Did Debezium actually capture it and process it? So that's Debezium in a nutshell and change data capture in a nutshell. And for those of you that may have been familiar with Debezium, I don't want to bore you too much with those details. Let's dive in now into those patterns that everybody is here to learn about today. And the first one we're going to talk about is the outbox pattern. The outbox pattern is basically aiming to solve one key problem. When we have a microservices architecture, we ideally need to be able to communicate between those microservices. And we need to make sure that we can communicate between those microservices reliably and consistently. We don't have access to things like two-phase commits typically or XA-type transactions. So we need to be able to have a way in which we can communicate across those service boundaries. Now, you might think, for example, I've got this e-commerce application where I accept this purchase order and I write it to my database when this purchase order comes in, and I'm just going to send an event to Kafka, and then that's going to notify my service, my shipment service to ship that order. But the problem with this is there isn't a distributed transaction or a shared transaction between your service and Apache Kafka. And I would argue even if there were such a capability, you probably shouldn't do it. Now, this particular type of approach is called dual writes. They lead to all types of inconsistencies and problems. What happens if you're able to persist to your database, but then you can't send it to Kafka because Kafka is unavailable? Maybe somebody stopped the server for some reason. How do you handle that situation? Or maybe you send the event to Kafka, but then the transaction where you were persisting that order to your local database fails and gets rolled back. How do you handle that? So the outbox pattern aims to solve precisely this problem. And as my good friend Gunnar Morling always says, friends don't let friends do dual writes. So with the outbox pattern, what we're going to do is we know that we can update our local database with no problem. And we know if there is a problem updating the database that it's going to get rolled back. So we can use this to our advantage by introducing a table inside of our local database called the outbox table. And if we think about this in real-world terms for just a moment, you can think of this like your mailbox. When you want to send a Christmas card or a birthday card to a relative or loved one, you prepare it, you put it in an envelope, and you put it in the mailbox, and the mail carrier comes along the next day and picks it up, right? Same kind of situation here with the outbox pattern with change data capture. So what you're going to do is the order service is going to persist to its domain tables, this order and its order line, and then it's also going to write an entry into this outbox table for delivery. And Debezium is going to recognize this particular change because we're only interested in this outbox table, and we're going to capture that change from the transaction logs. And we're going to deliver this event to a Kafka topic, and then our shipment service can react to this particular event and make sure that we ship this order. If we take a look at what this table looks like, you can kind of think of this from a perspective of domain-driven design. We have an aggregate type, an aggregate ID, an event type, and a payload. And these kind of represent, I'm sending an event for an order. The order number happens to be 123, and I'm wanting to notify that the order is created. So there's going to be a topic that will get created in Kafka that's prefixed with a certain prefix, but it's going to end with order created. And then this payload that we see here in this table is what's going to be part of that event's payload. Now you could serialize this column as JSON if you want. You can serialize it as a set of bytes. You could even pre-serialize it as Avro if you wish. And the idea and most important thing I think to take away from this, besides the fact that it allows you to have consistent communication across service boundaries, is it also allows you to be able to create a divide between your domain model and your event model. You can evolve those two models completely independent of one another, and that can be extremely powerful in terms of just making sure that as you're maintaining and updating and evolving one service, that you're not necessarily impacting another service. The next pattern I want to talk to you guys about today is called the Strangler Fig pattern. How many people have heard of this pattern before? Okay, a few people. Cool. The Strangler Fig pattern can actually be represented in nature. If we take a look here at this particular tree, for example, what happens is birds and other critters are going to take these seeds for these figs up to the top of the tree and place them on the branch, and eventually these seeds are going to affix to this tree. And what it's going to do is it's going to start consuming this tree, and these figs grow to the bottom and eventually root into the ground. And what you eventually see is not what you started out with. You see something completely different from what you originally had. And this is all happening at various different speeds. It's happening at various different points and parts on the tree. So you can kind of think of this as like it's incrementally happening, and it's happening over time. When we try to apply this into IT and technology, we can think about this in terms of migrating systems. I'm moving from a monolithic application to a set of microservices. So the idea here and the problem that we're trying to solve is we want to incrementally move from something that we currently have to something that's new. We also want to make sure that as we're doing this, that we're capable of supporting coexistence of what we had before and what we're moving to as well. And the last thing that we want to avoid is we don't want to be in the office at 12:01, everybody huddled in a corner when somebody presses the enter key, and everything, you're swapping from that old system to the new system, and everybody's sweating and hoping that it works. We don't want to have this. We want to try to minimize risk as much as possible. So with the Strangler Fig pattern, we can kind of go back to our old faithful example here of our e-commerce application. I have this monolith with these several modules, and what I want to do is I want to migrate this customer module to a microservice. Now you may have a proxy already in place, but if you don't, we're going to need to introduce a proxy in front of our monolith because we're going to eventually need to control what bits in our architecture are servicing different parts of this application as we move to this microservice. And once we have this in place, the first thing we need to think about is what's our data model for this customer service? Are we going to use the same database type rather? Are we going to use something completely different? What is our data model going to be like? Is it going to be completely different from what we started with? And as we make those decisions, we can then introduce a CDC pipeline in play to populate this new data source that we're going to use for this microservice. And we'll talk about in detail in a moment all of the different things that we may need to do as we discuss things like, is the data model changing? Am I moving from one database type to another, and so on. But once we have that data model, let's assume we have it in place now, we're populating and keeping this data model for this customer service up to date by using change data capture. So everything that's coming into our monolith application is being constantly replicated to this new database. Now we can start focusing on writing our customer microservice. And we're going to start doing this by focusing on things like read operations first. That's the least disruptive, if you will, in this process. And once we have all of our read operations written and ready to go and they've been tested, we can actually implement and turn those on by reconfiguring this proxy to service those read requests from this microservice. And this all works because we're using change data capture to make sure that that database that's supporting our customer service is being kept up to date. Now, once this is all working, we can start working on those write operations where we're doing those pushes back into the database. And once we have those done, we can turn those on, and we find ourselves in an interesting dilemma. As you can see, I've shaded out the customer module over in the monolith, and that's on purpose. We haven't removed it. It's still there, and there's a reason for this, and we'll cover why in a moment. But the dilemma is now we are servicing all of our read and write requests from this microservice. But what happens if our monolith application still needs information about customers? How do we handle this situation? Well, it's quite simple. We add another CDC pipeline that's now responsible for doing the inverse. It's responsible for taking all the changes that we're now making in this microservice and pushing those back into our monolithic applications database. And we can do this in such a way that if any other module needs that information, they can have access to that information and they're none the wiser. Now, what is the benefits of the strangler fit pattern? The most important benefit is, in my opinion, we're doing things in baby steps. It's really, really important. We're able to incrementally move from what we currently have to what we want to move to at any rate we choose. We also have the ability to pause and stop at any particular point in time, evaluate whether we're on the right path, make decisions if we need to make any changes, and then if we find that we either have made a wrong decision or if we find that there might be a bug when we turned on those write operations for our customer microservice, if we've done this all correctly and in a good way, we can very easily just revert back to what we had before. No harm, no foul. And as I said, the most important thing that this entire pattern is trying to focus on from a business point of view is minimizing risk. Whenever you're moving from a new technology stack from an old technology stack to a new technology stack, there's a certain amount of risk. When you're moving from a monolith application to microservices, there's a certain amount of risk. And all of our managers are always interested in what is that risk factor. So anything we can do to minimize that will always help us be able to drive the fact that we want to innovate, we want to move to new things, but we can do this in a safe way. Now I want to take a look really closely at the CDC part of this because I think this is really important to understand why CDC plays such a key part in this particular pattern. I talked about the fact that we want to be able to move data from this old data store to this new data store. And the fact that the data model could be very different. Perhaps I renamed a field. Perhaps I chose to take some data and we want to represent this data in camel case instead of uppercase or lowercase, etc. Well, we can do all of those kinds of things out of the box with minimal configuration using what's called a transformation or a single message transformation. Now, this is a Kafka construct, a Kafka Connect construct, actually, and this allows you to do mutations to that change event in flight. This can be extremely powerful, and there are tons of built-in, out-of-the-box transformations available to you. If you want to mask fields, like I said, or you want to drop fields, add fields, etc. Now, I'm showing that I'm putting these transformations on the source side of these pipelines. But you don't necessarily have to put them there if your business use cases don't require them to be there. Maybe you want to put them on the sync side of this pipeline because you want to have the data inside Kafka to represent the source system instead of the sync system that would happen if you were putting it on the source. But there's another interesting component here by introducing both transformations on both sides of this pipeline. Perhaps you have sensitive data. There's a social security number in a table, and you want to make sure that social security numbers aren't leaked or made available in their raw form. And you may not necessarily be encrypting these inside the database, but when you end up putting this data into Apache Kafka, into a topic, you might want to make sure that that information is encrypted. And so by using transformations, you can encrypt this data as it leaves the source system. It will reside in that Kafka topic in an encrypted form, and then you can use a transformation on the sync side to decrypt that data as it's going into the destination database. But all of these transformations are operating on a record-by-record basis, which typically when you're looking at change events, that's exactly what they represent. It's a change to a specific row in a specific table. But maybe you want to actually change the data model entirely. Maybe you want to represent the data in your new microservice as an aggregate of what you had in the monolith application. Or perhaps you want to go the other way. Perhaps you have a situation to where the data in the monolith is not granular enough and you want to actually turn a single record into multiple records on the destination side. You have access to what's called Kafka streams inside Apache Kafka that allows you to do precisely those types of things. So this entire pipeline with change data capture provides you tons of different functionality to mutate that data at any particular point in the pipeline, depending on what your business requirements happen to be. Now, the last pattern that I want to talk to you guys today about is called the saga pattern. And the saga pattern is a pattern that's aimed to try to solve long-running business transactions across microservice boundaries. So we've talked about being able to consistently communicate with microservices using the outbox pattern. And we've talked about how we don't want to use distributed transactions in our architecture, but you may still have a need to do some kind of collaborative communication across microservices. And you need to be able to have a solution in place to where you can achieve this collaboration and arrive at a consistent outcome every single time. And again, we need to be able to do this without using things like XA transactions or two-phase commits. And we want to ensure that in the case of a failure, that we always can arrive at a consistent and correct outcome of that saga. So if we go back to our Old Faithful again, this e-commerce application, I've got these 3 microservices. And we're receiving this order, and if we focus purely on the happy path for just a moment, the order gets received by the order service, and it needs to collaborate with the customer service to perhaps make some kind of determination. Are there too many pending orders for this user in play? Or do we need to increase the user's credit limit? And whatever that check happens to be, we're going to assume for a moment that that check succeeds. And once it does, then we need to consult the payment service to accept the payment details for this order. And if we assume, if everything goes according to plan and the payment service accepts those payment details, we can mark this order as accepted. And that's all well and good. And working with a happy path is usually the easiest thing. It's working with the non-happy path or the failures that are usually the most difficult. And so if we take this particular example and we talk about, well, what if I gave the wrong credit card number? How do we handle this? In this particular case, what we're going to have to do is we're going to have to do a step called compensation. So as we consulted this customer service and increased the credit limit for this user, we're going to have to reverse that operation. And so when the payment service, when we provide incorrect details to the payment service, once we've released this credit, only then are we capable of marking the order as rejected. Now, if we look at this from a CDC point of view, this is where it gets extremely interesting, because we're going to combine the saga pattern and the outbox pattern together to handle this complex orchestration of events across microservice boundaries. Our user is going to request that they want to place an order. When we receive this request, we're going to have to talk to the customer service and say, hey, is it okay to accept this order? And the way we're going to do this is write an event into our outbox table, the dependency that will pick up and send to a Kafka topic that our customer service is listening to. Our customer service will then respond with either a success or a failure. And let's assume for a moment that it's the happy path, so it was successful. That successful response is going to come back to the order service. And then the order service is then going to consult the payment service and say, hey, I need to process this payment. And if the payment service successfully accepts the payment details, it will send its response back. And then the order service can continue by marking that order as failed. That order as accepted. But if we think about this from the failure point of view, what does this look like? It looks exactly like this. This order service is going to consult that customer service. It's going to request the credit limit approval, and it's going to succeed. And then we're going to send those details over to the payment service, and it's going to fail, at which point we need to compensate. And we will then send a request to our customer service to compensate for that failure, and then the customer service will respond. So wrapping this up today, I really hope that a few takeaways from this is that you see that change data capture is an extremely powerful tool in order to drive event-driven and microservice architectures. The patterns that we've talked about today help simplify extremely complicated business processes and use cases. And if you are not familiar with Debezium, I hope I've been able to share with you the power of Debezium today and the fact that it's a wonderful open source CDC solution that supports a wide range of databases. And if you are familiar with Debezium and you would like to see the Saga pattern implemented as a out-of-the-box component, please let us know. You can contact us on debezium.io, and you can reach us on our mailing list or our Zulip chat from there. And here are some links if you guys want to take a screen grab of this. The first three are some blog posts that describe these three patterns that we talked about today. And the last link is to our examples repository. We have examples, including the Outbox and Saga patterns, in our examples repository. But if you want to be able to learn more about Debezium, or you want to see how Debezium interfaces with other types of technologies like Kafka Streams, for example, there are examples there in that repository that you can step through and see how that all works. And with that, folks, that's it for today. Any questions?
Is it using the JSON patch for the differences in the JSON? The one screenshot that you showed where there is operation view. So is it using, how is the differences calculated?
The before and the after state depends on the database in question. So most of the relational databases are able to provide us this upfront, and then we're able to just put that data into that type of format. Databases such as, say, for example, Oracle provides us a SQL statement that has like an update statement with set columns and then a where predicate, and then we have to parse that SQL to determine those values. If you're talking about something like MongoDB, for example, the format in MongoDB is very different. And that's just because in MongoDB, there isn't a schema, if you will. It's a schemaless data store. And so typically in this case, if you're working with, I think it's Mongo 4.2, perhaps, I think, or higher, then we're able to get some full document views out of Mongo, which is all in a JSON string, essentially. So if you want to be able to see what like the full document is, you do have access to this, but it isn't in the same format as the relational databases.
Does your example link has the MongoDB example in there?
The MongoDB, there are some in there for MongoDB. For example, there is the Outbox example has the MongoDB there. There is also an example for using what we call the event flattening transformation. There is a transformation specifically for MongoDB, and then there's a different one specifically for relational databases. But those examples are there. Mm-hmm. Yes? That depends on the database, actually. So we don't have anything like that, unfortunately. I can tell you that, for example, the load that you would see on something like Postgres or MySQL is significantly less than what you might see on an Oracle database. But that's just because of the APIs that are being used. Some of those APIs are just a bit more potent in terms of requiring CPU and resources. Yes?
In case if the Kafka is unavailable for Debezium itself, what kind of retries it does to make sure the event is posted?
I'm sorry, I didn't hear you.
In case if Kafka is unreachable for Debezium,
yes.
So what kind of retries it does to make sure the event is posted?
Yeah, so in that case, what happens is each of our connectors are putting all of these change events into a bounded queue inside the connector implementation itself. And that queue gets pulled by Kafka Connect on a given interval. And if Kafka Connect pulls information out of that queue, but then is unable to deliver those events to Kafka, then the offsets for that connector will not get updated because the offsets only get flushed and committed on the Kafka side. And so in this type of a situation, if you were to say stop Kafka Connect, work on Kafka, and then bring everything back up, then the connector is going to start where the last flushed commit occurred to Kafka. But if you fix Kafka, for example, and Kafka Connect is still running, Kafka Connect will just continue to retry sending until Kafka is available. Any other questions? Yes?
So for the embedded engine, it's built in with Quarkus, right?
It's what?
It's built in, is an extension from Quarkus.
Not the embedded engine, no. The only thing that is using Quarkus is the Devnexus server component to provide that runtime. The embedded engine itself is just simply a wrapper around running those connectors that allow you to just be able to embed it inside any Java application.
Last time I checked, I saw somewhere it's mentioned like Camel extension has that embedded engine in there.
There are Camel connectors that do embed the embedded engine in them in order to ingest change events from source databases, yes.
Okay, so would that be an option to
If you're a Camel shop or you are more familiar with Camel, absolutely. It would be no different than if you wanted to use, say, Apache Flink's CDC solution that does exactly the same thing. But yes. Mm-hmm. Yes?
Are you using other message queue instead of Kafka?
Say that again, I'm sorry.
Can you use other message queue instead of the...
Yes, you can actually. That's where you would need to use something like the Devnexus server, and then you could actually send those change events to any other messaging infrastructure that we support. So Event Hubs, Google Pub Sub, etc. All of those are available to you. Let's see. I can just show you really quickly. So you can see here are all of the available adapters to different messaging infrastructures that are available with Devnexus server. So one thing about Devnexus server, just to mention, if you are on Kubernetes, for example, and you want to use Kubernetes eventing, you can use Devnexus server there specifically for that. Yes, sir.
So the connector for the PostgreSQL, right?
Yes.
The connector be reading the complete WAR files, or is it only specific to a table? For example, if I want to replicate only one table, right, out of 150 tables.
Yes.
So how does the connector work?
So for PostgreSQL, what we do here is we create what's called a replication slot inside the database. And then on the replication slots, you can actually create what's called a publication. And if you want to create the publication for all tables, you can do this. In which case, what will happen is the replication slot will send changes for all tables over to the connector. And then inside the connector's configuration, you define what tables you're interested in. And then we would filter it on the connector side. But if you want to minimize the traffic over the wire to Debezium, you could actually configure that publication to only specify that table of interest. And then when the logical replication protocol runs inside the database, it will only send events to Debezium based on the tables that you defined in the publication. Any other questions? If not, thank you guys so very much. I appreciate it. Great questions today. If I could, though, thank you. If I could, if you guys could indulge me for one moment, I do have two questions for you guys, though. Since you guys asked me a bunch of questions, I would love to be able to get your insight on this. Are there any connectors or any infrastructures or application databases, etc., that Debezium doesn't support that you would like to see? And if you don't know, you could just say, hey, I would like to see it for Oracle, and we could say, hey, we do have this. But is there anything that you would like to see that might help you in your organization? Elasticsearch? So that's an interesting one because one of the developers on the team had a question. There is a sync connector for Elasticsearch, and he was curious if you have used it and if there are any pitfalls to the connector. So if you get a chance to use it, and if you find that there is something that's not there that you need, let us know. We'd love to be able to get that feedback.
Yeah, because I'm looking at these, I'm not sure, but these are for like,
These are the messaging infrastructures.
right, like for the messaging infrastructure part, but I'm curious about that. The database part.
Yeah, so that would come back to this slide here. Let me find it. Here, for example. Oops. Oh my goodness. This mouse is so sensitive. So these are what we currently support. Now, there are, for example, ScyllaDB. They have created their own CDC connector based on Debezium, but it's not under the Debezium portfolio. But these are the ones that are under Debezium's portfolio. So when we do releases, these are the ones that we release to.
Okay, so any plan of supporting more?
We would love to. Like if there are databases that you would like to see support for, we would love to be able to know what those might be, and we could certainly look to see, bandwidth, resources. Could we kind of knock that out for you?
One of the previous slides had Elasticsearch.
Yeah. You're talking about the very first one that I talked through, right? This one. Yeah. So these are sync connectors on the right. These are not Debezium connectors. These are connectors that are implemented by other vendors, but there are sync connectors to being able to get data out of Kafka to these various different data stores. I'm sorry? That would be interesting. I think that one has come up once before, so I'll take that back to the team and we can talk about it. Yes? The trace files? Which kind of...
Not directly reading the Oracle table, but can it read Oracle trail files that are extracted?
Are you talking about the redo and archive log files? Yes, that's exactly what we do. So during the snapshot phase for any of these relational connectors, that's the only time that we read the physical tables. So we gather the schema for those tables, and then we grab all of the data in those tables to generate change events. From that point forward, we're not reading those live tables anymore. We're actually using whatever the change data capture functionality is from the database. For Oracle, it would be we use LogMiner, and LogMiner would read those archive logs and those redo logs. For something like SQL Server, we would use the capture table instances, and that's what we're reading from.
How about in case of DB migrations, like adding new columns to the DB? So how does it capture some?
We do capture that. Now, every connector works a little bit differently. So for example, if you are using the Oracle connector with its default mining strategy, it seamlessly works. But let's say you were using it with the online catalog strategy, there is a little bit of lockstepping that you have to do in terms of making sure all the old events have been processed before you do the schema change. There's similar schema evolution steps that are required for SQL Server because of how that CDC technology works. But generally, for most of the databases, it's completely seamless. Yes, back there. Yeah.
I saw a lot of databases that are OLTP, but is there any use case that you guys are trying to solve for, like Snowflake, for example, which is more like an analytics database?
No, not at this time. I know recently there was a discussion about TIDB, which I think is something very similar. It's like a time-based type of database. But there isn't anything, but I can certainly take that back to the team that there could be interest there.
Yes, you mentioned about introducing event hub. But there are the limitation for the message in the event hub. How can you solve this kind of issue?
What kind of issue with the message?
The event hub. You just have different event hub.
Yes.
So the event hub has the size limitation. Right?
Yeah.
You need a running file.
So in that particular case, unfortunately, you just have to make sure that the size of whatever it is that you're sending for that single event doesn't exceed that size. We don't have a way of being able to handle that natively, but we do try to batch to those types of messaging infrastructures. But in terms of the individual messages themselves, if there is like a 1 megabyte or 2 megabyte size limitation, then you have to work around that. And the same thing is kind of similar with Kafka. Kafka has its own limits, but unlike, say, for example, event hubs, you can configure this in Kafka so you can increase it if you need to. Anything else? Any other questions? Oh, no, that's fine.
The incubating section or instead like incubating Cassandra, does that mean we shouldn't, like, is it not stable?
That's an interesting question. I would say that for Google Spanner, that is the case, because that one just came out. Google's been working on that for quite a few months, and it finally got published, I think, the last quarter of last year. So it's still quite new, and it's still getting a lot of community bake and feedback. But things like Vitesse and Cassandra have been out there for quite a while. They probably could be considered non-incubating, but a lot of it has just kind of is driven based on how much of the community is being involved in those connectors, and how much are we seeing that users are actually using them. So maybe once we start seeing that users are using them a bit more and they're getting a lot of traction, then we could promote them from non-incubating. Yes?
What kind of the data isolation you have in the, say, do you all kind of data isolation?
What kind of isolation do we use? Is that the question?
For the relational database, they have a dirty read or kind of a dirty read.
So the only time you have to be concerned with isolation is during the snapshot phase. And most of the connectors have a connector configuration called snapshot locking mode, I think is what it's called. And so you can actually tell the connector, I don't want you to do any locking. I don't want you to use this type of isolation. I want you to use this, that kind of thing. So each of the connectors, depending on the way the connector interfaces with those tables, you have ways of being able to configure this. But then if you take, for example, Oracle, okay? Oracle doesn't require any of this because Oracle uses flashback queries to be able to get the state of those records from those tables at a given system change number. So there's no need for any particular type of isolation for that type of connector. So it really ends up being connector specific. But there are ways to being able to control that or set that as you need. Does that answer your question? Okay. Any other questions? Great. Thank you guys so very much for the feedback. I very much appreciate it. Thank you.